and interval estimations. And they kind of go with the idea of the difference between discrete and continuous things. And what we want to do is we want to find an estimate for where values may lie. And so the first thing we're going to look at is the point estimate. And so point estimate is we're looking for a single value for a population parameter. And so, but we've only measured a sample or a statistic. And so the most unbiased, there are other ways to estimate things, but the most unbiased estimate of the population mean, which I've been using the Greek mu for, is the sample mean. Right? And so here's a single number that we're using to represent the population. And so if I take a sample, it's an estimate. It's an estimate of a point value. Now what I've done here is I've grabbed some data, and so I'll read the data description here and I'll show it to you. And then we'll do some calculations with the data. Let's go over here. There we go. And so what I've done here, and this is in the slide also, is I've put in 40 values of 40 values of data. And so it says a researcher is collecting data about a college athletic conference and its student athletes. A random sample, which is this 40, is selected, and their number of hours they spend on athletic activities for 1 week are recorded. And we want to find a point estimate for the population mean, which is the mean number of hours spent on required athletic by all of the student athletes in the conference. Now, this isn't all. This is 40. This is a sample. And so what I did here is I came over and I did the average of B1 to B40. So my data is in B1 to B40. And that returned 21.05 or 21.1. However, we want to kind of try to talk about that. And what we're going to do is we can say, you know, that all of the students, student athletes at this convention have an average of 21.1, 21.05 athletic hours per week. And we could say that about the population, but it's going to have some problems. And just remember, symbolically, this is what a sample average is. I add up all my samples and I divide it by the number of samples I've taken. Now, remember how I said we've got a couple of different things we use, right? We have the math formula to tell us kind of what we're doing. We have the idea of an average or a mean being one measure of a middle, right? Mean, median, and mode. And we're saying a population has some mean. Well, our sample mean should estimate it. And this is a point value. It's a distinct value, right? 21.1. Put it on a number line. It sits there. And I've got, 200 people. Some will be here. Some will be here, right? In fact, I might not have anyone in there that answered 21.1. And so point values, we kind of want to say, well, how good is that estimate? And so what we want to do is we want to then really extend that idea, and we want to talk about what we're going to call an interval estimate. And an interval is a range of values. Used to estimate a population parameter. Now notice the game here. We're estimating a population parameter. We're taking sample data and we're talking about the population. And so what we're going to do is we're going to talk about finding what we'll sometimes call a margin of error. So we'll think about, we have that 21.1, and then we have some interval, and on either side of that, we'll be able to collect people, and we'll say, well, 21.1 given a margin of error. Well, the question is, how wide do we make this? And so what we need to do is we want to determine how confident do we need to be that the true mean will fall in here. Now, if I wanted to be 100% sure, then in my margin of error would cover, well, they could be from 0 to, let's see, 24 times 7, right, is 8, carry your 2, 168, because that's how many hours there is in a week. So I could say, man, it's 21.1 with a lower end of 0 and an upper end of 168, right? That will get everyone. But it doesn't tell me anything about the population. And so what we want to do is we want to have some reasonable confidence of this interval. And what we're secretly hinting back to is we want to be able to talk about how much stuff we can wedge around our mean without, and have this the chance, the probability of the true mean being in there. It becomes a probability distribution. And so when we talk about confidence, we're talking about, how certain or how sure or how likely it is that our true mean is in there. And so we're going to call this the level of confidence. And it's the probability that the interval, so it's the probability that the interval we're going to create contains the population parameter. Notice how we moved from probability being this esoteric thing and how things get generated, and now we're talking about, well, what are the odds that the thing we're looking for is in what we measured or saw? And so obviously high confidence values are important. And so we're going to use the z-score idea, and we're going to talk about the probability inside 2 points. And these points are going to be what we're going to call critical values. So they're critical values. And if you're outside the critical value, you haven't fallen within our region. Now the thing is, this is symmetric. So if I want to be, let's say, 90% sure, or if I want a C value of 0.9, then inside of this bit here, I need a probability of 0.9. That means over here has to be 0.05, and over here has to be 0.05. We already did this with z-scores. This is done for us. Right? We already know on a z-table where we can find things here. In fact, what we can talk about here is, because this is symmetric and we're looking at on both sides, your book will give this formula, 1/2 1 minus c. Tells you how much is in here and how much is in here. Well, I can look this z-score right up on a table. If I look up 0.05 on a table, I get a z-score of negative 1.645. Well, this is symmetric, so I know my positive z-score is 1 point. And I now have the z ranges that I want. And this can work with any percentage. In fact, normal confidence levels are usually want to be 90, 95, and 99% certain. That's how confident we want to be what's in our interval. And so because we had this thing where we mapped the whole normal distribution back to z-scores, we already know these places in terms of z-scores. If I want 90% certainty, 5% comes before and 5% comes after, I know this value. It's always going to be this. So that's not too bad, right? We have something we always know what it's going to be. And so what then ends up happening is at 90% level of confidence, we have Z critical for the plus or minus Z scores are at 1.645. And we know these endpoints. Well, let's look at this in the terms of the stuff we're now talking about then. And since we now know we can map confidence levels back to these normal curves and how the normal is driving our sample, we'll talk about sampling error. And that's the actual difference difference between the point estimate and the actual population value. So my point estimate is X and my sample is mu. And so that's my sampling error. All right? This is what my sample measured. This is the reality. Generally, we don't know what that is. And this is going to change from sample to sample. But we can kind of use all of this together and notice that this hints at our z-score, right? Remember, z-scores was x bar minus mu over standard deviation of the mean times the square root of n. So what we can do is we can talk about making a margin of error. Some kind of range where we can look at. And so what we need for this to work is we need the sample to be random, and we need the central limit theorem to hold, which means the population is normal, or n is greater than or equal to 30. And you're going to hear these criteria are going to come up over and over again. That we need things to be random because we're relying on the fact that we're not biasing things by choosing them. That randomness is letting us jump back and forth, and that the central limit theorem holds so that things are that we can use these bell curves, these Gaussians, these normal curves, and these z-scores to talk about where our data is. And so the error, the margin of error, is the critical value. Now remember, we had a plus or minus critical value. And so we're going to have a plus or minus on error. And so what we can do is we can say, hey, let's leave the plus and minus out for right now. We have our margin of error is the critical value times the standard error of the mean, or critical value times the population standard deviation divided by the square root of n. And there are some things that this will become useful for the margin of error. So let's find the margin of error, and we're going to do it with the confidence interval we did before. And so we're going to do this two ways, and we'll look at the data there. So what we can do, if I pop it back over here, there's the data, is we're going to find the margin of error on this estimate, right? That our mean is 21.05. We want to know, of all the people attending the conference, what's the truth of it? So here's where we're at. All right, so let's find the margin of error, and we're going to do it for a 95% confidence. So let me come back here. So with that data from the slide there, I want a C equals 0.95. Well, that means if I look at my normal curve, I want 95% in here. That means 0.025 is here and 0.025 is there, right? Because I need a total of 0.05, 5% before and 5% after. So I can invert my Z function. I can do a Z inverse, or I can look up on a table, or I can do a confidence value. But my critical value is going to be negative 1.96. And we know we took 40 pieces of data. And we're going to say that the population has 2.3 hours as the standard deviation. We're going to say right now we know it. Later on we'll do some changes to this to see what happens when standard deviations of the population aren't known. And it has a lot to do with beer, but I'll discuss that later. But for now we'll say we know it. And so my critical value is 1.96. My population standard deviation is 2.3. And I had 40 in there. And so we're good to use. And so my standard error, or I'm sorry, my margin of error, when I plug all this in, is 0.7, on and on and on. And so we're 90% confident, 95% confident that at that 20.1, at 0.7 hours on either side, or 21.8 and 0.7 off, 20.4, I now have created an interval. I can say, and there's a couple different ways we can talk about this. We can say that we think the mean is 21.1. 21.1 or is it 20.1? Now I just lost where I wrote that. Where did I write that down? Oh, I'll just peek over here. 21.1. All right. Plus or minus 0.7. And this is how we kind of write it in the sciences. The book will do 20.4 less than mu less than 21.8. And it will do the addition and subtraction. In the sciences, we just say, hey, I could add that to one side, I could subtract it from the other. And so the 95%, there's a 95% probability the true value is in between these. And so notice what we did. We said, I want to be 95% sure my true value is within a range, and we've now found numbers. And so when I can say, hey, I'm 95% sure, I have a confidence level of 95% that the mean at this conference is 21.1 plus or minus 0.7 hours. All right, let's do a little bit here with our technology and let it help us here. So I'm going to show you in Excel what we need to do here. And so I put the function in here. We have a function called confidence. And so what I want to do here is I want to build the whole thing. So I've created my mean by saying average B1 to B40. I've got my mean. Well, now I want a confidence. And so I want to do a confidence of 95. Well, Excel needs me to do the subtraction of 1 minus 0.95. And we'll talk about that more. There's another thing called alpha. We could say this would be a 0.05 alpha level. There's different variables people use. Notice there were two sides to that curve, and so I could be talking about inside or outside of the curve. But for right now, I'll just say 1 minus the percentage I wanted. Remember I said I sometimes say percentages as decimal points. So 1 minus 0.95. Then we need the standard deviation, which is 2.3. And then an n, the number of samples I had. So if we put it all together here, I have my confidence, 1 minus my confidence value as a decimal, the population standard deviation, and the number of samples. And there I get 0.71, right? We rounded to 0.7. But look what I can do here. I can build my interval. I can do my lower bound is going to be equal to, well, C1 is my mean, minus D1. And there's that lower bound. Then my upper bound is C1, equals C1 plus D1. And there I've made my confidence interval. And so, this is the best way to compute it, in my opinion, because if I change data in here, I'll get a new mean, and it updates everything for me. But we can also compute it on paper like we've done before. We can use different technology, but this is what the formula looks like for confidence intervals. And so we have the ability to talk about being certain of where our data is. And that certainty comes from things following a normal distribution. So that normal distribution and that z-score is very important for us. All right, well, I could come in here and I could make this confidence stricter. I said I wanted to be 95% certain. Well, what if I said, you know what, that's not good enough. I need to be 99% sure. I'm just going to come back in here. I want to change this to 99. Now notice and so see what I did here? I changed the 1 minus to 99%. The other data was the same. Still had the same population standard deviation. Still had 40 samples. And so now it's updated. My range is larger now. I have to include more numbers to be more sure. Right. If I want to be less sure, notice my range is smaller. It tightens up. The less confident I am, the more numbers I have. The more confident I get, if I want to be 99.99% sure, right? Almost, the wider the range gets. And so confidence tells us how sure we are that our mean is in there.